Okay, so for this question, we've got this marble that's colliding with a pendulum and sticking, and then that pendulum is swinging up in the air. And the stuff that we know, right, we know the mass of the marble, we know the mass of the pendulum, and we can figure out how high that pendulum swings up in the air. So they give you these little blue dots that are the center of mass of that pendulum, and that's where we should be measuring the height from. Now there's a couple ways you can measure that height. So you could actually lay the horizontal ruler down like this, and then you could put the vertical ruler up and actually measure the height. Or you could do something where you measure the length of this, measure this angle, and then do some right triangle trigonometry to figure out what this is. But essentially there's two different parts to this question. There's a conservation of momentum part, and there's a conservation of mechanical energy part. And we have to think separately about those. So we can use conservation of momentum to understand the collision here, to relate the initial velocity of the marble to the speed that the two move with together right after the collision. So assume conservation of momentum basically just during the collision, and then we can use conservation of energy to relate the height that the pendulum achieves to the speed that the system is moving with right after the collision. So again, what we know is the mass of the marble. I use a little m for that, the mass of the pendulum, and the height that the pendulum swings. And we're looking for the speed the marble has before the collision. So our conservation of momentum equation should look like this, right? Initially in the system, we only have the momentum of the marble. And then after the collision, the mass of the pendulum and the marble added together times the speed of them combined is going to be the momentum of the system, right? And these two should be equal to each other if we're assuming momentum is conserved. Now, the next piece is conservation of energy. So after this marble sticks, they start to swing up, and the two mass system together, I guess we can think of that as an object, has kinetic energy, and that kinetic energy will be transformed into gravitational potential energy of the mass Earth system as it swings up in the air, right? Because at the highest point, there's no kinetic energy anymore. So that's where we get this equation, and then just kind of plugging in some of the other variables, we get to here, right? So the kinetic energy of the two together is 1/2 the combined m times v squared, where v is the speed they have after the collision, right? That's this v here. And that should be equal to the gravitational potential energy in the system after it swings up. And notice that the masses cancel out, and we end up with this, where again, this v is not the speed of the marble. This v is the speed that the pendulum and marble have after they're collided. So in order to solve for the speed of the marble, we're going to have to get rid of this variable. And we can do that by coming up to our original equation, finding the v, and plugging that in here. Right, that brings us to this. And then to find the speed of the marble, we just rearrange this equation. Right, so first what I did was since this is just a division, we can move the squared onto the numerator and denominator separately. So that's how I got here. And then I just rearranged, so I multiplied both sides by 2, and this m plus m squared to move the 2 and the m plus m squared over here. And then divided both sides by m squared and put that down here, and then took the square root. So that gets me this. And then just simplifying a little bit gets us to here. So that's how to do the first part. The second part, just to check this result, is pretty straightforward. You just do something like this. Right, all you have to do is measure a distance and a time, and that should get you the velocity of the marble as it's moving through the air, because it moves it at an approximately constant velocity. All right, so I hope this was helpful, and if you have questions, let me know.